Okay, so everybody please have a seat. And our next lecture is going to be the highly expected one from Professor Edward Witten. As the most eminent theoretical physicist of the time, Professor Witten has done a lot of work, have been solved a lot of problems that I'm not even capable of introducing. So let's just directly hand over to Professor Witten. Welcome.
Thank you. I know this talk is going to be a little bit of an outlier in a condensed matter school. I hope it will be at least of some interest to condensed matter. And since I know there are some string theorists here, I hope to say at least a little bit that might be new to the string theorists, so they're not really terribly new. I will, though, at least start with the model that's celebrated in condensed matter as well as particle physics. And this goes back to the work of Polyakov in 1975. In those days, asymptotic freedom of four-dimensional gauge theory was a new discovery, and the problem of understanding the infrared dynamics of four-dimensional gauge fields leading to confinement in QCD was a very fresh problem and also very challenging. Polyakov proposed a simpler problem that he claimed with the analogous, that was a nonlinear sigma model in 2 dimensions with the target space being an n-dimensional sphere. So you introduce n plus 1 scalar fields xi that obey a constraint that the sum of the squares is 1. And the action is, well, the obvious kinetic energy of these fields, which would be a free theory if there were no constraints. But the constraint forces the fields to take values in a curved space. And for example, if you assume that the x's live at the north pole in the sphere, and you expand around that point, then the curvature of the sphere will give interactions. So the model is an interacting model, and Polyakov showed that the model is asymptotically free, similar to Yang-Mills theory in 4 dimensions. Asymptotic freedom means that under the renormalization group flow to the infrared, that is to long distances, lambda effectively becomes bigger. If t is the parameter that measures renormalization group time, so t is sometimes called mu d by d mu, t is the logarithm of the scale parameter. The renormalization group equation is that d lambda dt is n minus 1 times lambda squared. So at n equals 1, the n sphere is just a circle, which is flat, and there's no renormalization group flow. If n is bigger than 1, it's positively curved, and Polyakov's basic result showed that positive curvature corresponds to asymptotic freedom. Now, as in 4-dimensional gauge theory, it follows from this the following 2 facts. First, well, as I said already, the theory is asymptotically free in the UV. In other words, as t goes to minus infinity, which corresponds to the UV, lambda would start out at 0. Sorry. Well, I won't try to correct it. There's a slight misstatement in what I said, but I won't try to correct it. The second statement is that perturbation theory does not suffice. So the first statement means that this model actually corresponds to a cutoff independent quantum field theory. As you flow toward the infrared, you go to strong coupling, but that means in the UV you started at weak coupling. So the theory had an almost Gaussian fixed point in the UV, which enables you to say that it's a well-defined quantum field theory. Second fact is that since you're flowing to strong coupling as you go to the infrared, perturbation theory does not suffice to determine the physical properties of the model. So as you go to the infrared, you'll leave the regime where this one-loop formula is good, and more generally, you'll leave the regime where you can calculate by perturbation theory. However, methods are available that are absent in the 4-dimensional case. That's a misprint. So this 2-dimensional problem has methods we don't have in 4-dimensional gauge theory. There's a 1 over n expansion that's good if n is large. And also, it was discovered a little later by the Zamolodchikovs that the model is actually integrable. So the model is much better understood than 4-dimensional gauge theory, and it's well established that it flows to a massive infrared trivial fixed point, which is what we believe 4-dimensional pure gauge theory does. But in that case, we mainly rely upon computer experiments or real experiments in the case of SU3 gauge theory. For this problem, we have analytical methods. Now, Polyakov had considered a sphere, and then other papers were written with various special target spaces. But about 5 years later, Friedan considered a completely general two-dimensional model in which the target space is any Riemannian manifold W with any Riemannian metric Gij. So if the x's are local fields that correspond to coordinates functions on W, and now I'm going to use unconstrained coordinates. So there will be no constraint on the x's, but there will be a non-flat metric Gij. The model with the sphere could be put in that form by using the constraint to solve for one of the x's in terms of the others. Then, in terms of the unconstrained fields, the action would take this general form. So the action is what's called the action of a two-dimensional nonlinear sigma model. Nonlinear because the target space is a manifold W that generically is not flat space, but some nonlinear space. And this is taken to be the action. So Polyakov had considered the special case that W is a sphere of radius 1, and the metric was a constant times the round metric on the sphere. But Friedan considered a completely general case. Now, as in Polyakov's example, perturbation theory is a good approximation if the metric is large. Large means that you take any metric and multiply it by a big constant, or as I'll do it, divide by a small constant lambda. So if you take any metric but multiply by 1 over lambda when lambda is very small, that makes the metric very big. So the target space becomes very big, distances are very large. And the target space locally is almost flat. The theory would be free if it were actually flat. It can be locally approximated by a flat manifold when lambda is very small. So there's a perturbative regime where G is very big or lambda is very small. And Friedan computed the leading correction to the classical behavior in that perturbative regime. And, well, I take some liberty with the normalization, but Friedan computed the one-loop approximation to the renormalization group flow and found this, where Rij is the Ricci tensor. So the sign tells you that if the Ricci tensor is positive, the metric, as you flow toward the infrared, becomes smaller. So remember, I explained that a big metric is the region where the theory is almost free. As we flow toward the infrared, the metric becomes smaller. The sign is opposite to what Polyakov had just because Polyakov wrote a flow equation for lambda, where I'm writing it for G, and because G is 1 over lambda, that reverses the sign. So Friedan found that the flow is by the metric changing by a multiple of the Ricci tensor. For example, as I said already, if the Ricci tensor is positive, the metric becomes smaller as t increases. That generalizes Polyakov's result for the round sphere. The round sphere is a basic example of a Riemannian manifold with positive Ricci curvature. And so Polyakov's result that the model flows in the infrared towards strong coupling is a special case of this more general result for any Ricci any model with positive Ricci curvature. So if Rij is positive in the infrared, one eventually flows to a region in the space of metrics in which the one-loop approximation breaks down. On the other hand, if Rij is positive, you can hope, conversely, that in the UV, the model was asymptotically free, and therefore that you have a sigma model that actually is ultraviolet complete, true quantum field theory. Now, fixed points of the renormalization group are very important in physics, of course. Friedan's computation at first sight seems to show that the condition for a fixed point is Einstein's vacuum equation, Rij equals 0. In a different history of the world, this observation might have been the starting point for the discovery of string theory. It didn't happen in our planet because string theory had actually been discovered prior to Friedan's work. But if there are lots of planets out there where physics was developed, there might well be some where a computation like Friedan's was the initial spark that led to the discovery of string theory. Now, Friedan did a one-loop calculus. Friedan's computed the renormalization group flow in the one loop approximation. But of course, there are higher loop corrections that you could compute. And the higher loop corrections are polynomials in the Riemann tensor and its derivatives. The reason for that, maybe I should have said a word about how Friedan did the calculation. The simplest way to do such a calculation is what's called the background field method. So you pick a background classical solution. G0, let's say, is a classical solution. Then you write, oh, sorry, I should call it X0, because my code my field's X. Then you write X as X0 plus X quantum. And then you compute Feynman diagrams describing quantum fluctuations around the background field. And the vertices in the Feynman diagrams are found by expanding the action around a classical solution. But in the case of this sigma model, when you expand around a classical solution, the vertices will come from derivatives of G. But if you do the computation in Riemann normal coordinates, the derivatives that come in will all be Riemann tensors and their covariant derivatives. So even before computing, it will be manifest that the renormalization group functions are built from the Riemann tensor and its covariant derivatives. So in the one loop approximation, Friedan computed this result, and what comes in is the Ricci tensor. But in higher loops, you'll get generally covariant expressions that will be built from the Riemann tensor and its covariant derivatives. So they'll be imaginable as corrections you could have in a more general theory of gravity. So you could have been motivated in a different history to ask, is there an interesting alternative to Einstein's theory in which the vacuum equation of Einstein, which said that Rij was 0, is replaced by the condition that the beta function of a two-dimensional sigma model vanishes? Well, the answer to the last question is yes, but with some important caveats. First, from this point of view, it's not clear why the alternative theory has a better ultraviolet behavior than Einstein's theory. Remember, Einstein's theory does not have a good ultraviolet behavior. It's unrenormalizable. There's a quite different formulation of the theory, which is the one that had been discovered before Friedan's work, string perturbation theory, that shows that the alternative theory that we get here does have a better ultraviolet behavior than Einstein's theory. But from the point of view of a perturbative analysis of the sigma model, that's completely unclear. Second caveat is that to make this idea work, you need additional fields beyond the metric tensor G. You really need infinitely many fields, but in today's lecture, we're only going to include one additional field. And the third caveat is that vanishing of the beta function is an oversimplified statement of what the right condition is. So there's a sort of a yes answer to the question of whether there's an interesting new theory where the beta function replaces the Einstein equations, but there are these slight corrections to the statement. Vanishing of the beta function leads to scale invariance, but the right condition is Weil invariance or conformal invariance rather than scale invariance. Well, what is the difference between scale invariance and conformal invariance? Scale invariance of a theory defined in flat space is invariance under a rigid rescaling of the coordinates. Now, these are the space-time coordinates, and today I'm discussing a two-dimensional quantum field theory. So we're working in a two-dimensional space-time with one space, one time coordinate. And we also have a target space whose coordinates I've called capital X. For today's lecture, it could have any dimension. But we're working in a two-dimensional space-time in studying this sigma model. So there's one space and one time coordinate, but since I use T for normalization group time, I'll write tau for time in this two-dimensional world. Okay. In defining scale invariance, we could have any number of spatial coordinates, so I wrote X vector, but in our actual application, we'll only have one. Scale invariance is invariant under a rigid rescaling of the coordinates, where you take the coordinates and rescale them. Conformal invariance is invariance under a conformal rescaling of the metric of the space on which the theory is defined. So in writing the sigma model action as I did, I implicitly chose the metric to be the Euclidean metric, delta alpha beta. But we could have used an arbitrary metric, G alpha beta, and then the sigma model action would have been this one, which reduces to this in the case of a flat space metric. And since we could define the theory for any metric, well, okay. Okay. So precisely in 2 dimensions, this action classically is Weil invariant. Weil invariance means that it's invariant under Weil rescaling of the metric for an arbitrary scalar function phi. So this operation of a local rescaling of the metric by a space-time dependent function is called a Weil transformation or Weil rescaling of the metric. Precisely in 2 dimensions, the sigma model action is Weil invariant. To check that, notice that in 2 dimensions, G is a 2 by 2 matrix. So its determinant is a quadratic function of G, and therefore scales with twice this exponent. But the metric tensor with indices up is the inverse metric, which scales like the inverse e to the minus phi. So precisely in 2 dimensions, the scaling of the square root of determinant G cancels the scaling of G alpha beta, and the action is Weil invariance. So Weil invariance implies invariance under what's called the conformal group, which is the group of coordinate transformations that change the metric by a Weil rescaling. An example of a conformal transformation that isn't an isometry, that's not part of the Poincare group, is the scale transformation that we discussed already. It changes the Euclidean metric by a Weil transformation. So a rescaling of the coordinates is an example of a conformal transformation, but the group of conformal transformations is larger. In D space-time dimensions, for D bigger than 2, is the finite dimensional group SOD2. It's finite dimensional, but it's bigger than the Poincare group, and it's also bigger than the Poincare group plus scale transformations. But in 2 dimensions, which is really today's focus, it's an infinite dimensional group. To see that it's an infinite dimensional group, we could start with the Minkowski space metric, minus d tau squared plus dx squared. But I introduce light cone coordinates, tau plus x and tau minus x. So I write ds squared as minus du dv. And this representation of the Minkowski metric makes it obvious that up to a Weil transformation, the metric is invariant under arbitrary reparameterizations of u and v. You could take u to be an arbitrary function of a new coordinate u tilde, likewise for v. And the metric in the new coordinates is just du tilde dv tilde times a function. And assuming this was an invertible change of coordinates, the function is positive, so it's e to the phi for some Weil rescaling. So in 2 dimensions, Weil invariance implies invariance under an infinite dimensional group of coordinate transformations. Above 2 dimensions, it's a finite dimensional group, but one which still is bigger than Poincare transformations plus scale transformations. So in short, scale invariance follows from Weil invariance, but Weil invariance is a potentially stronger condition. Now, since Friedan had found the one-loop renormalization group equation to be what I've written, naively a fixed point of the renormalization group is a Ricci flat metric. That is one that satisfies Rij equals 0. So, as I essentially said before, perhaps I didn't say it quite clearly enough, naively the Einstein vacuum equations are the condition for a fixed point of the renormalization group in this one-loop approximation. But Friedan observed that that isn't quite the whole story. In general, we should only care about the metric of the target space up to a diffeomorphism of W, and therefore if the change of the metric under changing the renormalization group scale can be interpreted as resulting from a diffeomorphism, then this is a fixed point in a more general sense. So the assertion that dg dt is the change in G induced by some vector field V is that dg dt is di vj plus dj vi. And that's equivalent to the renormalization group flow if the Ricci tensor can be written this way in terms of a vector field. So as Friedan observed in the one-loop approximation, the properly interpreted condition for a fixed point of the renormalization group is not that Rij is 0, but that Rij can be written this way. Now, this more precise interpretation of the condition for fixed points might discourage us from the idea of using the renormalization group of the sigma model as a substitute for Einstein's equations. Because while the equation Rij equals 0 can be derived from an action, namely the Einstein-Hilbert action of gravity, and is a sensible equation of motion for field theory, at least classically, that's not true of this equation. This is an equation for a pair consisting of a metric tensor G and a vector field V, and that equation for the pair can't be derived from an action. So that means that you won't have Newton's law of equal and opposite action and reaction, which follows from being able to derive the equations of motion from an action in modern terms. So it seems if we're more careful about what is the condition for a fixed point, we no longer have a sensible starting point for a modified theory of gravity. Just for fun, I'm going to give you an example of a spacetime that obeys the more general equation and not the Ricci-flat equation. It's a two-dimensional example with this simple metric, which is the cylinder of revolution. It's a sort of semi-infinite cigar. When r is large, so theta, let's say, goes from 0 to 2 pi, but at given r, the circumference of the circle is really 2 pi times tanh r. But for large r, the tanh approaches a constant. At r equals 0, it goes to 0. So this is the metric of what you could call a semi-infinite cigar, which I drew rather crudely here, but I didn't, in this picture, capture very well, didn't show very clearly that the radius of the circle asymptotically goes to a constant. As I've drawn it, it's still increasing where I stopped the picture. And this is a fun example because it's actually a Euclidean version of a two-dimensional black hole. If you analytically continue this metric to Lorentz signature, you actually get a two-dimensional black hole. Anyway, going back to the relation between scale invariance and conformal invariance, it can be described this way. In general, in quantum field theory, the stress tensor is conserved. I'm calling the stress tensor T alpha beta, and I'm assuming we might be on a curved spacetime. So I've written the conservation law in the covariant sense with covariant derivatives. In flat space, we'd replace ordinary covariant derivatives with ordinary ones, and this would be an ordinary conservation law. In curved space, it's not really an ordinary conservation law. It describes the flow of energy momentum from matter to gravity. Now, Weyl invariance or conformal invariance means that the stress tensor is traceless as well as conserved. The reason for this is that by definition of the stress tensor, well, let's recall the definition of the stress tensor. So the stress tensor is the variation of the action in a change of the metric. But if you want to get this trace of the stress tensor, you don't want to consider an arbitrary variation of the metric. You consider the variation of the metric to be a scalar function times the metric. Well, okay. From what I've written here, it follows that the variation of the action, well, by definition, the variation of the action is the variation of the metric times something, and that something is called the stress tensor. But here we want the variation of the metric to be a scalar function times the metric. So the formula would say that the variation of the action is the scalar function phi times the trace of the stress tensor. So immediately from the definition of the stress tensor, Weyl invariance is equivalent to the stress tensor being traceless. What's the corresponding condition for global scale invariance rather than vial invariance? Well, global scale invariance is a condition that we only state in flat space. So I take the two-dimensional metric to be delta alpha beta, and I look for a conserved current that will generate a scale transformation, delta x equals epsilon times x, where x's are the space-time coordinates. And we find that, well, first we want the stress tensor to be conserved, but we want its trace to be a total divergence for some current S alpha. And if these two conditions are satisfied, then we find that there is a conserved current, which is T alpha beta x beta minus S alpha. So the trace of the stress tensor being the divergence of something enables you to define a conserved current, and that conserved current generates scale transformations. So vial invariance says that the trace of the stress tensor is 0, but scale invariance just says that the trace of the stress tensor is a conserved current. Now, in Friedan's case, this was the condition for a fixed point over the renormalization group. A fixed point means that when you change the scale, the theory is invariant. So a fixed point, by definition, is the condition for scale invariance of the theory. So the equation Friedan described corresponds to scale invariance. And you can show, actually, that if the sigma model beta function, which was Rij, can be written this way, then scale invariance holds with an S that is constructed out of the vector field V. And that's a current which in the sigma model generates a reparameterization of the target. So the conserved current that goes into this criterion for scale invariance is the current operator in the sigma model that generates this reparameterization of the fields of the sigma model. So to summarize, scale invariance, the trace of the stress tensor is a total divergence. Vial invariance, or conformal invariance, the trace of the stress tensor is 0. Now, there's one more thing I should tell you, which is that there's a special case. Okay. Suppose first of all, the trace of the stress tensor is the divergence of a current. And let's suppose that this current is itself a gradient. So that's the special case where the trace of the stress tensor is actually the Laplacian of some operator. That case is going to be important in this lecture, so I'm going to explain something for which I didn't write a slide. There's something called an improved stress tensor. You define a new stress tensor, which is the old one, well, you subtract a term, d alpha d beta minus delta alpha beta times del squared of phi. The term which I've subtracted is chosen so that it doesn't affect conservation. I hope you can all read what I'm writing on the blackboard here. Can you, somebody in the back, can you see it? Okay. So I took d alpha d beta minus delta alpha beta del squared. You can check that this is still conserved, but it shifts the trace of the stress tensor. The trace of the new stress tensor is the trace of the old one plus something. So in general, if we find that the trace of the stress tensor isn't 0, but it's a divergence, that will only give us scale invariance. But if it's the divergence, if it's not just, if S itself is a gradient, so the trace of the stress tensor is the Laplacian of something, as I wrote here, then you can define what's called an improved stress tensor that's actually both conserved and traceless. So there's a special case of this where you actually do recover, after all, conformal invariance, but you need to improve the definition of the stress tensor. That's going to be important in a bit. Now, okay, so I've told you about Friedan's, Polyakov's work, and then about Friedan's work. I jumped ahead a little bit to tell you what some later authors said about Friedan's work. But there's another story that was happening at the same time. By coincidence, at almost the same time Friedan was doing the work I've described, the same equation, which from our point of view describes the normalization group evolution of a family of metrics on a manifold, was introduced independently by the mathematician Richard Hamilton. Hamilton was not studying quantum field theory. He was hoping to, he called this the Ricci-Flow equation, first of all, and he was hoping to prove the Poincare conjecture by using the Ricci-Flow equation to evolve any initially chosen metric on a 3 manifold W to a simple one that could be used to analyze the topology of W. The Poincare conjecture says that if W is compact and simply connected, then it's a 3-sphere. And Hamilton was hoping, okay, the 3-sphere is, it's not difficult to prove that the 3-sphere is the unique simply connected manifold that obeys Einstein's equations with a positive cosmological constant. So Hamilton's idea roughly was that he would start with any metric on W, flow it by this equation. He argued that that would tend to simplify the metric, and he hoped that in the infrared it would flow to a simple metric he could understand and use to prove the Poincare conjecture. Now, Hamilton was also interested in this more general equation considered by Friedan, which he called the Ricci-Salaton equation, which he also generalized it to include a cosmological constant, but which I won't talk about. Ricci-Salotons were important for Hamilton because singularities generated by Ricci-flow were the main difficulty in carrying out his program to prove the Poincare conjecture, and he showed that Ricci-Salotons control the behavior near singularities. Hamilton also showed that singularities involve what he called ancient solutions. An ancient solution is one that can be described on a semi-infinite time interval where t is in the range from -infinity to 0. For physicists, these correspond to asymptotically free theories that are expected to really exist as cutoff independent quantum field theories. So it's amusing that the asymptotically free condition, which is important in physics, was also important for Hamilton. By the way, near the beginning of the talk, I stumbled and got confused when I was trying to say this. But when the metric for the sphere, for example, was becoming smaller as t became more positive, that means it would become bigger if you go back toward the UV. And as it becomes bigger, perturbation theory becomes better and better. And so we would start at infinite radius at time -infinity, where infinite radius for the sphere corresponds to the free theory or asymptotic freedom. But for Hamilton, those were the ancient solutions associated to his singularities after some rescaling that he described. So Polyakov's example of the round sphere is a prototype of an ancient solution, and actually it was an important example for Hamilton. Now, going back to physics, by 1984 or 5, the normalization group flow of Riemannian metrics was understood to be important in string theory. It was understood that to get conformal invariance in the sigma model, and not just scale invariance, we need to consider the special case of the Ricci-Salaton equation, in which v is a gradient for some real valued function phi. I kind of explained that here. Here I said it should be a gradient on the world sheet. But if v is a gradient in the target space, the corresponding current is also a gradient on the world sheet. So this criterion I explained here corresponds to this in the case of the sigma model. So there are a couple of ways to describe the physical meaning, but one way to describe the physical meaning is that phi, which is called the dilaton of the string theory, is an extra coupling that can be added to a two-dimensional sigma model, the action being then this one. Same action as before, but I've added another term. R2 is the scalar curvature of the two-dimensional metric G alpha beta. I call it R2 because the target space also has its own Riemannian curvature, and in particular Ritchian scalar curvature, which appeared in some formulas, and which I just called R. So R2 will be the two-dimensional curvature. So these authors added another term, another field and another term to the sigma model action. Now, an immediate objection you could raise is that you want to do quantum field theory in flat space when R2 is 0. So why do we care about this term? The reason we care about it, even if we're working in flat space, is that the stress tensor is defined, as I told you, as the variation with respect to the metric. And this new term will contribute to the stress tensor, even if you're only interested in a flat metric, because if you vary with respect to the metric, you start at a flat metric, but vary, in first order, R2 will not be 0. It'll be roughly the Laplacian of the correction to the metric you've taken. And then by integrating by parts, you'll get a correction to the stress tensor involving derivatives of phi. So if you're only interested in the theory on a flat manifold, adding this term is equivalent to using a different stress tensor. But I explained here why we might be interested in a different stress tensor. I explained that, scale invariance means the trace of the stress tensor is a divergence. But if S is actually a gradient, so this trace of the stress tensor is the Laplacian of something, then we can improve the stress tensor to make it conserved and traceless. And a conceptual way to account for that is that when you have this function phi, you could add another term to the action, and adding that extra term will tell you to use a different stress tensor, because the variation with respect to the stress tensor evaluated at a flat metric is now different. So the story I said here amounted to saying that we can restore, if it's the case that the trace of the stress tensor takes this particular form, then we can restore conformal invariance or Weyl invariance by adding this extra term to the action, which will give us a stress tensor that's conserved as well as traceless in the special case of a flat worldsheet. So if V is the derivative of phi, then the equation becomes this one. And actually, this semi-infinite cigar I drew, sorry, I didn't realize it was so far back. This semi-infinite cigar, oh, here it is. This cigar metric actually satisfies the equation with V being a gradient. So it satisfies this form of the equation. So we have if we have this extended model, the new coupling, if we have this extended model, the condition for Weyl invariance is modified by this extra term. And this is now the equation, Weyl invariance is now equivalent to a modified Einstein equation and also an equation for phi. Now, unlike the more general Ricci-Soliton equations in which we do not impose Weyl invariance, these equations can be derived from an action for the pair G and phi. The action is this one. It's not completely obvious, but the Euler-Lagrange equations for this action can be written this way. And the action is called the low-energy effective action for string theory, at least in the case that only these two fields, G and phi, are considered. In general, one includes yet more couplings in the two-dimensional sigma model, and therefore more fields in spacetime. But for brevity, I will only consider G and phi. So the condition for conformal invariance is that these functions vanish. These functions are called beta functions in this context. So beta g and beta phi should both vanish. The condition for scale invariance is that instead beta g and beta phi are equal to the change in g and phi generated by some vector field V. Now, in a paper written in 1988, Joe Polchinski elucidated the relation between scale invariance and conformal invariance. Actually, some of the things I've already told you were in that paper. But, well, anyway. For today, apart from some things I've already said, the most important result that Polchinski proved, he proved that in general, in 2 dimensions, for unitary quantum field theories with a discrete spectrum, scale invariance always implies conformal invariance. In the context of sigma models, the hypothesis of a discrete spectrum holds if the target space is smooth and compact. It's important that it should be compact. If it's not compact, for example, in Rn, the wave function can spread throughout the target space, and you get a continuous spectrum. But a compact target space gives the sigma model a discrete spectrum. So Polchinski proved that scale invariance implies conformal invariance in 2 dimensions for theories with the discrete spectrum. The generalization above 2 dimensions was difficult, but eventually an argument was found in 4 dimensions. It's actually tricky to just state it properly, but let alone prove it. As far as I know, in 3 dimensions, there's no known proof. So Polchinski proved that in the case of a compact target space, if this is true, then in fact this is true for some scalar field phi, and the model is Weil invariant. Now, Polchinski's proof showed that the problem is closely related to the Zamolodchikov-C theorem. The Zamolodchikov-C theorem deals with the following question. Is the renormalization group flow irreversible? So intuitively, you might believe it should be irreversible, because intuitively, the renormalization group involves integrating out massive degrees of freedom to get an effective theory for lower energy degrees of freedom. And integrating things out, you would think, is irreversible. So intuitively, long before, Zamolodchikov proved the C theorem in the 80s, but people had suspected there might be such a result years before. Well, Zamolodchikov, I should say, proved it in 2 dimensions in the 80s. So, for example, in the one-loop approximation to a sigma model, the question is this. Take the Ricci flow equation. Does it have solutions with a non-trivial t dependence that are periodic in t, possibly up to a diffeomorphism of the target space? So if you flow with respect to this equation, could you ever come back to the same metric? So Zamolodchikov in 1986 provided an abstract argument that gives a very general no answer to this kind of question in 2 dimensions. Again, the analog in higher dimensions was more difficult, but by now there are answers in 3 and 4 dimensions. Polchinski adapted Zamolodchikov's argument to show that scale invariance in 2 dimensions implies conformal invariance, assuming the spectrum is discrete. Now, recently I revisited these questions using arguments due to Perelman as part of Perelman's work completing Hamilton's program on proving the Poincare conjecture. Perelman's construction had been elucidated and slightly extended by these authors. I had a concrete motivation for wanting to do this, which involved a particular class of 2-dimensional sigma models in which the relation between Weil invariance and scale invariance was known to be subtle, and I wanted to understand it more explicitly. But more generally, I was curious about what Polchinski's somewhat abstract argument means near the classical limit. In other words, Zamolodchikov and Polchinski had rather general abstract arguments, but one would think that near the classical limit there would be something more concrete, and I wanted to know what it was. By the classical limit here, I mean a large manifold in which the Einstein equations, coupled to a scalar field, the dilaton, and possibly other fields, are a good approximation. Now, Perelman's series of papers in which he proved the Poincare conjecture using the Ricci flow began with the new proof of the C theorem in the context of sigma models near the classical limit. So you might ask, why did he care about the C theorem? Well, the idea of Hamilton's program was that under Ricci flow, the metric should evolve towards simplicity. Technically, after removing or evolving past some singularities that occur, which are related to the Ricci solitons I told you about before. However, if there were periodic solutions, it would mean that you go around and around and never get simpler. So had there been periodic solutions, that would have been a very strong obstruction to Hamilton's program, or Hamilton and Perelman's program of proving the Poincare conjecture. So anyway, Perelman began his papers with the new proof of the C theorem. So I want to explain Perelman's proof of the C theorem for sigma models, and then I'll explain how you tweak it just very slightly and prove the relation of scale invariance and conformal invariance for sigma models near the classical limit. So the usual one-loop effective action for G and phi is this one. So for simplicity today, I'm only considering G and phi, but you can include additional fields like the so-called B field or the gauge fields of the heterotic string in this discussion without changing anything. The formula has become longer, so I didn't want to include more fields. This is enough to illustrate the idea. But it works for any low energy effective action in string theory. Now, the first thing you'll notice here is that the kinetic energy of phi has the wrong sign. There's a minus sign there. The kinetic energy for the metric actually has the right sign. In Euclidean signature, minus r is the correct sign of the Einstein-Hilbert action. So a sphere has negative action, for example, because r is positive. But the dilettante has the wrong sign of the action. I haven't included other fields, but if I included other fields, the other fields all occur with the right sign of the action. In the string effective action, there's only one field that comes in with the wrong sign. Now, that doesn't make the theory unphysical. Einstein's action has the same property as observed a long time ago by Gibbons and Hawking. So Einstein's action has a minus sign, just like I told you here. In fact, as Gibbons and Hawking pointed out, the conformal mode appearing in the metric, in other words, if you write the metric as a fixed metric times a Weil factor, phi appears in the Einstein-Hilbert action with the wrong sign. And that's actually one of the reasons that the Euclidean path integral for gravity is not so well understood as we would wish. In the string theory version, we still have this kind of phi. We also have this one. So as written, it looks like we have two bad fields. But in that two-dimensional space, there's only one wrong sign field. In other words, the kinetic energy for these two modes, the signature 1, 1 with only one negative eigenvalue. So the string theory case is neither better nor worse in this respect than the Einstein case. In Einstein gravity, Gibbons, Hawking, and Perry suggested to deal with the problem by a Wick rotation, phi going to I phi, which roughly corresponds to maximizing the action as a function of phi instead of minimizing it. Carrying this idea over to string theory, one might arrive at Perelman's idea of roughly maximizing the action as a function of phi to obtain a well-defined, well-behaved functional of the other fields. To understand in what sense we can maximize the action, we note that the action can be written this way. This is elementary, but I don't think it's very well known among string theorists. So this formula is actually equivalent to this one, probably after integrating by parts, where del squared is the Laplacian. Now, we can't usefully literally maximize S as a function of phi because the maximum would be where phi is plus or minus infinity, depending on the metric. What works better, as Perelman showed, is to maximize S under a constraint that this expression is 1. So we incorporate the constraint with the Lagrange multiplier. So the effective action becomes the usual action minus lambda times the constraint, which I can write this way. And now you see that if you, well, you want to extremize this with respect to phi and lambda for a fixed metric. But when you extremize with respect to phi, you learn that e to the minus phi is an eigenfunction of an effective Schrodinger operator. Except that I wrote lambda too many times in this equation. There's a misprint. Erase this one. So the Schrodinger operator is minus 4 del squared minus r. And lambda is the eigenvalue. So e to the minus phi, of course, is positive, and the constraint means that it's normalized, and it's an eigenfunction of an effective Schrodinger operator, which is this with the lambda erased. Well, this Schrodinger operator is the standard Schrodinger operator, the Laplace minus Laplacian plus a function, and that kind of operator is familiar to anyone who studied quantum mechanics. And as you all know, the ground state is the only wave function that has no zeros. And it's real because the operator, it can be chosen to be real because the operator is real. It can be chosen to be positive. The normalized positive ground state is the unique positive eigenfunction of the Schrodinger, positive normalized eigenfunction of the Schrodinger equation. So therefore, the extremum of the extended action, including the constraint, is unique, and moreover is a maximum with respect to phi under the constraints. So now I'm going to give Perelman's proof of the C theorem. You vary the action with respect to G, keeping fixed this measure. I meant to have a minus sign there. Okay. You keep fixed this combination where I want a minus sign there. And so the variation of the action with respect to G is e to the minus 2 phi hat times the beta function of the metric. There's a similar formula for variation with respect to phi, but we don't need it as we'll be evaluating the action at the maximum with respect to phi, where the variation vanishes. So an equivalent statement to this one is that under any variation of the metric, keeping phi fixed, the variation of S is this. It's the variation of G times the beta function of G times the measure. The measure was kept fixed in doing the variation. Now we just complete the argument using the renormalization group equation for delta G. The renormalization group equation says that dg dt is minus the beta function. So the t dependence of the action evaluated at the constrained maximum with respect to phi is ds dt equals minus the square of the beta function for G. That's strictly negative unless beta G is 0. In other words, it's strictly negative except at a fixed point of the renormalization group. So therefore, there can't be any non-trivial. There's a monotonic function. The function S is monotonic under renormalization group flow. S is the C function of Perelman. What Zamolchikov's C function was a function that's monotonic under normalization group flow and constant only at fixed points. And Perelman, this simple argument shows that S has that property. You take the string theory effective action, maximize it with respect to the dilaton, and you get a C function. So that was Perelman's version of the C theorem. S is strictly decreasing along any non-trivial flow. The nature of the argument is that it automatically extends to higher orders in sigma model perturbation theory. All we needed to know was that the action had a unique extremum as a function of phi keeping fixed G, and that the variation of the action with respect to G gives the beta function. And the second statement is known to be true, although it's not completely trivial. It's far from trivial. The first statement is automatically true given that it was given what happened in leading order. Now, we'd like to extend this to prove that scale invariance implies conformal invariance. Conformal invariance means that the beta functions vanish, but scale invariance means they vanish up to the combined effect of an infinitesimal diffeomorphism generated by a vector field V. To prove that scale invariance implies conformal invariance, all we need to do is to use the fact that S is invariant under diffeomorphisms. Invariance of S under diffeomorphisms means that, okay, I'm writing the formulas at the maximum with respect to phi. So I don't vary with respect to phi because we've maximized with, in particular, extremized with respect to phi. If I vary the metric, the change in the action would be delta S delta G times delta G. So if delta G is induced by a vector field, then because S is diffeomorphism invariant, we get 0. So invariance of S under diffeomorphisms tells us that 0 is the integral of the beta function times dv, divj plus djvi. If now we substitute the condition of scale invariance into the condition that said that the action was diffeomorphism invariant, we learn that 0 is the integral of the square of the beta function. So the beta function vanishes, and therefore in this framework, scale invariance implies conformal invariance. In other words, if this equation was satisfied with some v, it's also satisfied with v equals 0, is what we proved. So I carried out this discussion for the fields G and phi only. The closed bosonic string, which is effectively what we've been discussing, has one more massless field, a two-form field B, corresponding to an additional term in the sigma model action. I omitted this field today. Including it just leads to similar but longer formulas without changing anything essential. And the same is true if you include the gauge fields of the heterotic string. If we include higher loop contributions to the conditions for Weil invariance, we get corrections to the low energy effective action, giving an expansion that's valid at long distances. Fundamentally, there are two regimes in which we know how to calculate what happens in string theory. If the fields are possibly strong but slowly varying in space, the dynamical equation of motion is conformal invariance of the sigma model. That's what I've tried to explain today. If the fields are weak but possibly rapidly varying in spacetime, we do string perturbation theory. The two approaches agree when they're both valid, weak and slowly varying fields. We don't understand what to say when the fields are strong and rapidly varying. And a possibly related fact is that we don't have any general understanding of what string theory means, in the sense that Einstein's theory incorporated the principle of equivalence. There's no analogous conceptual explanation of what string theory means. Thank you.
So just from the beginning of the talk, in Polyakov's example, I was getting a conceptual picture that asymptotic freedom is coming from how sort of locally flat things are, and then going away in the other limit, for that particular example.
In that example, yes. Well, asymptotic freedom. If you take any Riemannian manifold and scale it up, locally it's flat, and the sigma model becomes weakly coupled.
Is there a lesson that's fair to take about that asymptotic freedom in general, or is that conceptual picture really specific to this example?
Well, you could say this story, I'm not totally sure I understand the question, but you could say the picture is similar for gauge theory, as you would see best in lattice gauge theory. So in lattice gauge theory, the lattice field is a group valued field, but the action has 1 over a coupling constant in it, which has the same effect as if you scaled up the size of the group manifold. So asymptotic freedom, recoupling, you see the group manifold is curved, but a free theory corresponds to an abelian gauge group, which would be flat. So asymptotic freedom for gauge fields is the statement that you can approximate SU2, for example, in the ultraviolet by a flat Lie group, U1 cubed instead of SU2. So it's somewhat similar. That's the best I can do by way of answering, but I might have missed. Well, I'm not sure if I answered the question or not.
That's helpful, thank you.
So in this new proof of, or this alternative proof of the seed theorem, the function that's decreasing is some effective action.
Yes. Yes.
Well, is there any nice interpretation of that? Usually I think of effective action as being constant under RG.
Well, it was, first of all, I want to stress that this alternative proof is less general than the other one. The abstract proof is good for all sigma models with discrete spectrum. The alternative is only good near the classical limit. Although near the classical limit, it applies to some cases with singularities and so on, where the other one wouldn't be good. Sorry. Just repeat the question quickly or remind me.
Usually when I do RG, I think of the partition function or the effective action as being constant. Here it's monotonically decreasing.
This is not the effective action of the two-dimensional theory. It's the space-time effective action of the string theory, but maximized with respect to the dilaton. Alternatively, it's the ground state energy of this effective Schrodinger operator. Where string theory differs from your experience with conventional theories is that there's a two-dimensional world. There's an auxiliary two-dimensional sigma model, which we studied. But what we were really interested in, as string theorists at least, Polyakov was interested in the physics on the two-dimensional world. As string theorists, we're interested in physics in the target space. So the action we considered was the effective action of the target space theory. But its meaning for the two-dimensional theory is a little bit mysterious. But it does have the property that when maximized with respect to the dilaton, it becomes a C function of the target space, of the worldsheet theory, of the two-dimensional theory.
Thank you.
Yeah, so you said that conformal invariance is equivalent to scale invariance up to some diffeomorphism. Is that diffeomorphism of the target space or of the worldsheet?
Conformal invariance is stronger than scale invariance. What I said at the beginning was that vanishing of the Ricci tensor in general only gave us scale invariance. Because it was, well, what did Friedan calculate was the beta function. And the beta function is the response to a change of scale. So yes. Even if it's clear to you, let me explain to everybody again. So by definition, a fixed point of the normalization group corresponds to something that's scale invariance. It's not obvious at all why it would correspond to something that's conformally invariance.
Yes, sorry, I was asking about the proof that scale invariance implies conformal invariance. You made this comment that that ultimately came from the fact that this S function was invariant under diffeomorphisms.
Yes, it's a diffeomorphisms of the target.
Diffeomorphisms of the target space, okay.
Because a diffeomorphism of the target is generated by delta equals V, let's say. And then that changes the metric of the target. As we learn when we study general relativity. And then the statement that S is invariant, and S was manifestly generally covariant. It was diffeomorphism invariant. So being diffeomorphism invariant means it's invariant under such a change of coordinates, which means that it's invariant under this kind of change of the metric. And that invariance of S, when written out in detail, gave us the statement that this expression in the second line is 0. And then if it happens to be that this quantity in parentheses is equal to beta g, we learned that beta g has to be 0. That was the proof that in this context, scale invariance implies conformal invariance. Yes?
This beta function flow of the sigma model is a renormalization of strings.
It's certainly true that conformal invariance of the sigma model is the condition for having a classical solution of the string theory. But the interpretation beyond that statement is a little bit unclear, I would say. Any other questions?
So let's thank Professor Witten again for this mind-blowing lecture.